Venkat Viswanathan received his bachelor's degree from IIT Madras and his PhD from Stanford. Before joining us, he is an assistant professor in mechanical engineering, Professor Viswanathan.
Thanks a lot, Jerry. Thanks to the organizers for giving me the chance to present this Andy talk. It's going to be very different from anything I've ever did, so we'll see how this goes. Okay, so I'm going to tell you a little bit about batteries and why they're now probably one of the most exciting areas of research, and how it plays into sustainable transportation, and one that you may not have heard too much about, which is sustainable aviation. And this all starts with humans. We're explorers. We'd like to travel, see places. This is a unique part of our human identity. We'd like to see places like this. This is the Maldives. We'd like to see places like this and like this, without that leading to this, right? So this is the big challenge, right? How can we enable all of what we would like to do, which is travel, explore, and lead the life that we lead, without it leading to issues like this? And so two key pieces in this is sustainable transportation and sustainable aviation. And sustainable transportation is something that is near and in sight. And one approach to sustainable transportation, we had Andy Stevenson from Tesla, who was here yesterday. And electric vehicles are one approach to sustainable transportation. Now, there's a caveat there that it's really important to ensure that the energy source for electric vehicles essentially provide electric power through batteries that are inside the electric vehicles. And the important caveat is that the energy source needs to be from a renewable source. And so we saw yesterday Andy showing the Tesla solar roof tile. Apparently we can order it next week in 5 cities. Pittsburgh's unfortunately not one of them. But in principle, if you have solar roof tiles, which gives you a way to get solar energy, now if you could store that in your battery pack, that provides a pathway for sustainable transportation. But there is a problem. The problem is that these cars typically don't go as far as we would like them to go, which we heard Marcia call the range anxiety today. We also have a second issue associated with that, which is Tesla decides to solve this problem by oversizing the battery pack, which is essentially just adding more batteries and making the battery pack much, much heavier. Now, that leads to these batteries becoming extremely expensive, and you don't have a way for making a mass market car. And so the two issues are essentially closely linked, and a quantity by which we find this useful to characterize is energy density, which is the amount of energy you can store per unit volume or amount of energy that you can store per unit weight. And usually the two are often correlated. And so what I show here is a plot of energy density for many of the chemistries that you might know. Lead acid batteries, which was the workhorse battery for nearly 150 years, still has a huge market share, which is still used even in a Tesla for the starter battery. Then you had nickel metal hydride, nickel cadmium. Nickel metal hydride was the first battery of choice for the Toyota Prius models. And lithium ion, which has now sort of become the unanimous battery of choice for automotives, both in the context of hybrid electric vehicles and fully electric vehicles. And so we've been on an incredible ride for the last 25 years. 1991, Sony commercialized the first lithium ion cell. And we've been on an incredible ride with lithium ion batteries over the last 10 years, essentially improving 10% every year. But there's a general consensus that we've come to the limit of where lithium ion could take us. And lithium ion, when I say lithium ion, it is the sort of the standard variant of lithium ion that is used in cells today. And essentially, we sort of believe that we're hitting the bottleneck in terms of physical limits of how much energy you can store inside these lithium ion battery packs. And so there is an urgent need to radically change the approach to storing energy. And so of the alternatives available, there have been two attractive new battery chemistries that have been proposed. One is lithium sulfur. Sulfur is extremely cheap, so this gives us a pathway to both low cost and high energy density, and lithium air, or really lithium oxygen, and I will cover the lithium oxygen case in great detail. Now, a common element to both lithium sulfur and lithium oxygen is that it requires a working lithium metal anode. And so lithium sulfur and lithium air are sort of seen as the long-term strategy. In the near and medium term, there is a pathway forward where you could just have lithium metal anode substitute the graphite anodes that we use today, and you'll still get a 20 to 30% improvement in the energy density. And so that represents an attractive path forward. Now, the question is, why do we not have lithium metal anodes in our batteries today? And so I'll sort of give you a 30-second version of how a battery works. Batteries have anodes and cathodes. The anode is graphite, and the cathode is some kind of layered compound or some kind of host material that takes the lithium ions. In the fully charged state, the lithium ions are inside the graphite. And when you discharge the cell, the lithium ions move from the graphite anode to the cathode, where they would rather like to be. And the energy difference between having lithium ions in graphite versus the host material on the cathode is how you derive energy. Now, what you would like to do is to try and remove as much of the extra material as possible. The extra material in the anode is the graphite sheets, the graphene sheets. And so the holy grail is essentially to do away with graphite itself and just have pure lithium metal. Now, the challenge here is when you try and cycle lithium metal back and forth, which means you move it from the anode to the cathode, back to the anode, and so on, when you charge and discharge every single day, there are these mossy dendritic type structures, very similar to the structures that you've seen in snowflakes. Actually, it's the same underlying physics that goes on between these two cases. And so these dendritic structures often grow through from the anode to the cathode, and it creates a short circuit. And typically, when you have liquid electrolytes, that leads to fire and other unwanted things. And so the question that we are asking is, how can we enable a lithium metal anode and do that in a way where it is scalable and integratable in today's lithium ion manufacturing. The approach that we have taken, and one that's now being funded by DOE through the EERE program and ARPA-E, is to essentially rethink the way lithium metal is enabled. And the approach is to self-form, and the way we will self-form is to add strategically certain components in the liquid electrolyte that is used, and self-form a thin film that is coating the lithium metal, and the coating will have certain properties that can block dendritic growth. One approach is simply, you have a growing wire. If you put something really strong, then you can block that growth. That's sort of the obvious way to do it. Unfortunately, it turns out that when you try and make a material that is hard, it turns out that that does not allow lithium ions to move through as efficiently, so that remains a challenge. We've learned a second surprising way to do this, actually something that was inspired from geology, where in the context of phase transformation between two rocks. Sort of the same analogy is what happens with stalactites in rocks. There's a second regime, which is sort of density driven, where you actually can get away with a really soft material as long as it has a denser packing of lithium in it. And so it actually turns out that these two approaches, at least one of these things, we think is a way to enable blocking of these dendritic structures. Now, there's a second part that's required to enable lithium metal anodes, which is that as you cycle these batteries, this film, this barrier film will invariably crack. And so we need some mechanism to close this crack. And so that's sort of the self-healing part of our scheme, which is essentially to add some constituents in the liquid electrolyte that will immediately close the film once a crack develops. And so we think with this self-formed and self-healed approach, we can enable a lithium metal anode. This is a project that we have in partnership with 24M, which has really novel manufacturing approaches that essentially provides a pathway to hit $100 per kilowatt hour. So coupled with high energy density and low cost, we think this represents a real pathway forward for electric vehicles. Okay, so that's on the electric vehicles front. What happens when you want to think about sustainable aviation? And this is a real challenge. And so what do we do to enable electric aircraft? And I think it's really important to frame the question in the correct way, because it's really easy to convince oneself that electric aircrafts will never be viable, but that actually is not true. You can sort of run a back-of-the-envelope calculation. Jet fuels are 11,000 watt-hours per kilogram. We have about 20% efficiency of the jet engine. You have 2,000 watt-hours per kilogram. Best battery packs today that we have are about 200 to 300 watt-hours per kilogram. Right? This looks really challenging and daunting. But it actually turns out that when you have electric aircrafts, there are some new architectures that are possible. We learned about the first principles approach to thinking about designing things yesterday. And the key is when you do a design of an electric aircraft from the ground up, an electric aircraft will look nothing like an existing aircraft. The electric motors are really light, so what you would actually do is you would distribute the propellers. So distributed electric propulsion essentially gives you a factor of 4 reduction in drag. So you're already starting to sort of access 100 watt-hours per 1,000 watt-hours per kilogram of usable energy. So it's really important that we ask sort of the right questions, and it's essentially important to redesign the aircraft around it being electric. And so this is an analysis that was done. I would encourage those of you that are interested to read the paper by the researchers from NASA Langley. They've done a wonderful analysis and sort of outlined the targets that we need to hit for addressing sustainable aviation. Now, some of this is really hard, but some of the markets are accessible. And it's important to recognize that it's already happening. The glider market, there are already electric propulsion already integrated into gliders. Now, if you want to access general aviation, which also includes things like commercial business jets and so on, you need to access an energy density of about 400 watt-hours per kilogram. The best cells that we get from state-of-the-art, which could take the Tesla cells or things like that, they're somewhere in the 180 to 200 watt-hours per kilogram at the pack level. And with lithium metal, you can get to about 300 maybe, 350. But to reach the 400 to 500 range, you need a second change to the battery chemistry. And this actually exploits one of the unique things about aircrafts, which is that aircrafts have onboard oxygen systems. So what you could do is, if you could use the oxygen in an efficient way for the battery chemistry, then you don't actually have an additional component that you have to add. It actually can naturally integrate with the way in which the system is already built. And so in this case, it actually turns out that lithium oxygen batteries, so you use lithium metal that we talked about earlier, couple it with an oxygen cathode, and this represents a unique fit for electric aircraft applications. And this can actually reach energy densities to the tune of about 400 to 500 watt-hours per kilogram, and accessing the general aviation market. So you could think about electrifying planes that fly between 200 to 400 miles, which actually represents 90% of the flights that are taken today. All right, so how does a lithium oxygen battery work? It has a lithium metal anode, like we discussed last time, and a liquid electrolyte and some sort of porous material, and oxygen flows in from the tank and the lithium and the oxygen react to form lithium peroxide, which is a compound whose chemical energy is what you release out as voltage in the cell. Now, it turns out that lithium peroxide is one of the most reactive compounds known. And so what happens in this case is liquid electrolytes tend to react with the product formed, and so these batteries don't cycle very many cycles. And so the electrolytes in this case are the missing piece to enable lithium oxygen batteries. And here, when I say electrolytes, it is the liquid electrolyte that we're talking about. So the first part of the issue is that the electrolytes decompose, reacting with lithium peroxide. The second part, which we all know, is these liquid electrolytes are flammable, right? Which may be okay. We might be able to contain it in smartphones. We might be able to contain it in cars. When you are 30,000 feet above ground, you don't want any such issue to happen. So we would have to move beyond the state-of-the-art electrolytes. And so this was one of the challenges that I took on when I started my assistant professorship here. And we tried to completely rethink how we would go about doing discovery of electrolytes. Electrolytes seem really, really simple. There's only two components, a solvent and a salt. And all we want to do is to try and find a solvent and a salt that is stable and that can provide the functionality of transporting lithium ions from one electrode to the other electrode. It actually turns out that organic chemistry is extremely rich, so we figured this would be a challenge we can take on. But we quickly realized that organic chemistry is rich, but it's also challenging. So the opportunity that we thought also presented a challenge. And so the approach we took was to do a two-step discovery process, and this represents sort of a radical departure to how electrolyte discovery is done today. Electrolyte discovery today, even in the best groups, including the work that happens in sort of many of the most innovative companies in the battery space, is essentially try, change the electrolyte, try again, change the electrolyte, try again, and so on. Right? There's almost a lack of a physics or a first principles based approach to try and design liquid electrolytes. And so what we did was to try and take a data-driven approach, where what we wanted to do was to let data teach us organic chemistry and let physical laws emerge from the data. And so there's two parts to this discovery process. First part that we term as human-in-the-loop discovery, which is that we use all this data, and so now we have collected data for over 50 million liquid electrolytes. That's quite, I think it's been a really exciting effort, and this sort of has played into nearly everything that we do in the group. And as a result of having so much data, you have physical insights that come out naturally from the data. And so we've been working with some computer scientists to develop visual data exploration tools with which we can gain insights from the data. Now, that's exciting, but that only gets us so far, because what you can do is you can come up with a set of candidates that are good, but the real lithium-ion battery uses 15 different electrolytes in different ratios. Right? It's almost impossible for human intuition to be able to do this discovery process. And so the next generation of this, and this is effort that's actually being funded by the Toyota Research Institute and their new materials program, which actually will be announced tomorrow. They've launched a really exciting program, and this has allowed us to bring together a unique group of people. Jay Whitaker, who brings his expertise in high throughput experimentation. Our group, which we bring in expertise in high throughput computation, and our effort in data cataloging and data mining of liquid electrolytes, and Barnabas, who's in machine learning. And what we want to do is to essentially build an autonomous electrolyte discovery unit. What it'll do is it'll use all these electrolyte manifolds that it picks from the first step of our discovery process, which is essentially human-in-the-loop discovery. We find a few exciting candidates, and then we let the machine learning platform make decisions on how to discover and how to make the next, what is the next electrolyte to pick, and all the time updating the data and then feeding that back to the physical models that will guide the discovery process. And hopefully with this, we think we can solve the electrolyte challenge for lithium oxygen batteries. And with that, in 3 years, in collaboration with NASA and their flight center down in LA, we will demonstrate and explain in I think fall of 2019, which is powered by a lithium oxygen battery. And this is the distributed propeller concept that I talked about, where you have, in this case, multiple propellers that bring down the drag. The important ones are the one in the end, which bring down the trailing edge vortices that are present. And with this, you can demonstrate that electric propulsion is indeed quieter, more energy efficient, and environmentally friendly. Okay. With that, I will close, and I have to thank the wonderful students that I've had at Carnegie Mellon, the federal agencies for funding our research, our close collaboration with industry, which has helped shape my thinking, help shape the group's thinking. And finally, I would like to thank the Scott Institute for Energy Innovation. The seed grant program that has been set up is one that really provides funds at a time when you can grow ideas which sound far-fetched, but then with that support you can really crystallize these ideas and grow them into sort of full-fledged research programs. Thank you.